long title, and I didn't want to call this 6G just a utopia or a next generation challenge. And many of you might be actually working on these famous SAGIN or IGUS networks. The acronym is basically Integrated Ground Airspace Communications Networks. And Rahim touched upon this very briefly. And so in a way, I will now augment that particular aspect. And, my hope is that you'll be able to enjoy the sort of journey element of it. It's not going to be very deep technically. But again, many thanks for the invitation to Leila and Dunding, and also so many other friends on the committee like Bruno and Amjad, etc. And of course, research is always, obviously a collaborative endeavor. So this is, as you see, I've got many names on it. I couldn't put the whole communications team at Southampton University on it. But as I said, I am basically centering these discussions around this paper at the top, which was a survey type, tutorial type paper in the proceedings of the IEEE, and there's some other magazine papers and then more deep research papers as well. So Rahim has got the biggest toys in our field, guys, I have to admit, but there is a little bit of history of wireless in Southampton as well, because this is where Marconi for the first time ever presented or demonstrated the feasibility of wireless transmissions. So down here, obviously, many of you know the UK geography, so London is up here and Southampton is down here on Southampton Water. And that's the Isle of Wight. And from the western tip of the Isle of Wight, where there's a little plaque, Marconi transmitted across the Atlantic to Newfoundland in Canada. And so there's another plaque at the other side. So that's kind of the history of wireless in Southampton. But many of you have known my predecessor, Professor Raymond Steele, was a great innovator and highly revered figure in our community. Back in 2005, unfortunately, we had a devastating fire at Southampton, and so we've got this relatively new building, not as luscious as 6GIC, but we're at the top of the building, and below us is the famous Optical Research Center, which actually caused the fire 15 years ago. So we ended up on top of it again. But moving on, over the years, we look back in time first, because after all, every journey starts with the starting point. And so Gordon Moore, back in 1965, predicted the growth of our field in terms of integration densities. And we gradually, over the years, spectacular commercial success and spectacular innovations in electronics and signal processing, all hand in hand, basically. But we reached this sort of top right-hand corner where we actually have now nanoscale integration, and quantum effects starts to play a role. But today I won't be talking about those, other than just really saying that obviously in the olden days we ended up from the BRIC, which was the analog FM, the total access communication systems in the UK, and many other national equivalents across the globe. And today in India, you can get a smartphone around about $10 US, which is unbelievable, but it shows the power of large-scale integration and large-scale commercialization. Well, still on the introductions, but I've got this classic outline, and because this is supposed to be a networking community, so I will focus a little more on the networking rather than physical layer side of things. And as we move forward, I will just cut out a couple of future research challenges as well. So what is the motivation? Well, Rahim mentioned coverage. And indeed, if you look at the current 2G, 3G, 4G coverage in the UK, you see that there are very big coverage holes. And essentially, it's only the main arteries, the main roads, and the metropolitan city areas which are well covered. Now, of course, I haven't got a picture of Ireland, although it would be probably quite similar because Ireland is also quite a rural place. But if you look at the US, again, you know, you could actually fit the United Kingdom or at least the main island into this space here. And there's huge areas where there's absolutely no coverage. You can get lost in the mountains and you can get lost at sea, etc. And so we have to deal with the coverage improvements. Saudi Arabia is much of it is of course sand, but again the metropolitan cities are well covered and along the roads. You see here, I haven't mentioned that in the previous slides, but you would see that the color coding is that blue is the 2G, green is the 3G coverage, 4G, and then 5G plus. And so obviously now we are into the 5G era. Historically, the Nordic countries have had excellent mobile communication services. Indeed, they were the very first one in the world who actually set up international roaming, and they got together and they motivated the European community then to build the GSM system, namely the second generation mobile phone systems. So I'm almost done with this kind of motivation, but the coverage holes are huge. And of course, they really prevent the agricultural population, for example, from doing business. So it's stifling business. Look at France, how fantastic. I don't know how on earth they managed to come up with such almost ubiquitous coverage, but it's amazing. And that's what we would like to have right across the globe. I hasten to mention that, as many of you would remember, we lost these Malaysian aircraft a couple of years ago, in fact, 2 of them, and the black box was never recovered. So obviously aircraft communications is extremely important, not just for control, etc., but also for supporting passengers mid-flight, for example. And so this picture, which is again from the proceedings of our Tripoli paper I mentioned, really portrays this kind of space air ground integrated network where we have the terrestrial users. Obviously then we have in the post-COVID era, hopefully cruising will return to the world, and one of these big cruise ships might have 5,000 passengers on it, and so they only have access to satellite coverage, but extremely low rate and extremely expensive. But we have the layer of planes passing by, and I will delve into this in more detail as we go along. But then, of course, Rahim mentioned the satellites. And so a huge challenge for our community is to sort of have seamless handovers across all these different layers. And my main message is for today is really to look at the true multi-component optimization of these systems, where Rahim's famous triangle is part of that kind of KPI diagram, the spider diagram, which we all know very well, where we can juxtapose the different conflicting requirements of, for example, delay and throughput, or delay and throughput and power, and various other things as well. Again, more about this later as we progress. There's an awful lot of research on UAVs, but of course they also have their problems because they have to be charged all the time. And so actually sky platforms at 22,000 meters are more realistic than using these quadcopters. But of course they will play an important role in delivering Amazon packages, etc. And so we have to control them extremely tightly as well. They have to land on the balcony and deliver a packet, for example. And Dirk Pesch, my old friend, asked me an interesting question here. Why do we need 1 centimeter positioning, for example? And that would be one of the applications, apart from, of course, the other verticals as well. I know this image is really one where we could linger for hours and just talk through the intricacies, but I will delve into some of these in a little more detail. You find some readings, as I mentioned here, But the bottom line is the most important point here is that the planes at 10 kilometers would only have about 30 microsecond delay at the speed of light, and low Earth orbit satellites would be still all right for seamless communications, nearly lip synchronized video as well. But the geostationary satellites are not. And just go back for a moment, you see here that they are at 36,000 kilometers. So the delay would be 120 milliseconds, and people just cut into each other's voices all the time. So what I'm preparing the ground for here is really to talk about Pareto optimization as we go along, namely multi-component optimization. So these are the components on this exciting global communications picture. And so we have the terrestrial layer. Some of you might know the work which Slim Looney did on covering the remaining 4 billion, for example, because there's a lot of rural areas in the world where the only solution would be really to have a balloon, a tethered balloon to provide radio coverage. And of course, this is helium filled, so you don't need propulsion to keep it in the air, whereas the rotary wing quadcopters, for example, would burn a lot of power. So it's not very green, really, as such. And the sky platforms could be, of course, UAVs, which can be up for 6 months at a time. And then there's the civil aviation planes, which I will elaborate on in more detail. You find a lot more details on this again in this light-hearted magazine paper. But these are the high altitude platforms, some mock-ups, and I'm galloping here because it's not very technical, but it just gives you an idea as to how this could be implemented. And this is the one which can stay up for 6 months without maintenance. Then it would come down, and after some maintenance would go up again. You see the solar cells on top of the plane. And of course, it's not infeasible that we could at some stage also have some surface left for reflective surfaces. But today I won't be talking about that too much, just to really entertain you a little more in some detail now. So if you have access to the internet right now, which you obviously have because you're watching this program, so you could log on to FlightAware, and you could actually watch the planes as they, for example, land at Heathrow Airport or take off. And although right now their density is much lower than usual, but here at the left, you see Heathrow Airport. Here you see the European airspace and the North Atlantic. And maybe at the end, I will show you this in real time as well, because it's actually quite kind of interesting to keep watching the planes. So how realistic is it, to cover, the hitherto uncovered areas and improve the coverage? And so this is just a snapshot, a global snapshot, and you see that certain areas of the world are extremely well covered. And so that would be very feasible. But again, more details on this. I will probably use an example which is centered on Australia, because in Europe, the density of planes and in Americas as well, is extremely high. But even for Australia, this would be a feasible service to provide. So moving on, these are the ships, the cruise ships, and the greens are the cargo ships, the blues are the cruise ships. Right now, not so many. The red ones are the tankers, and then you've got the yellows, which are the fishing boats. So the interesting thing is that the ships cannot help the planes very much. And the other way around, however, is much more feasible. Because again, there would be a large user population on the cruise ships, for example. And even if people would have, relatively intermittent communications in sparsely populated areas, this would have certain benefits. So you might wonder, well, okay, how does this fit in with the 24 hours in the day? And you see here on the left-hand side, we have the number of aircraft, and down here we have the universal time. So GMT, right now UTC is the same as, oh no, it's actually, we have summertime coming from this weekend. Anyway, the bottom line is that you see the westbound flights are the red ones, and they start, sort of 8 in the morning, and their number increases to 240 or so. The snapshot was taken on the 29th of June in 2018. I will be using this date more frequently as we go along. And then you have the eastbound flights, which are the sort of lilac color down here. And the sum of the two are kind of, nicely equalizing each other. So you see here, for example, the green representing both westbound and eastbound. So again, I will look at this in terms of more detail as we go along, but you see that there's a large number of planes sort of flying around, which could provide either seamless or at least sort of intermittent coverage. So moving on to our second topic, basically the ad hoc networking scenarios. And, these scenarios have very different propagation properties. I won't delve into too much detail, but suffice to say that taxiing, at the airport occurs at maybe sort of just 0 to 15 meters per second. Then there's the takeoff when the speed increases to 150 meters per second en route, especially when two planes fly against each other, could be as high as 620 meters per second. And then again, coming down, holding and landing, taxiing, parking, very, very different propagation conditions. I will show you this in a bit more detail later on in terms of Doppler frequencies, etc., so that we are not unaware of the physical layer limitations. So how far can you transmit from a plane? Can you set up an ad hoc network across the globe amongst planes? And so one of the issues is, depending, of course, on the carrier frequency, that we have here a transmitter, and the transmitter cannot really easily transmit over the horizon. So planes have to be within something like 700 kilometers if they are at a 10-kilometer altitude. So that they can see that far. If they are higher up, then they would have a larger propagation distance feasible. So here I have a little probability density function here, which indicates that if I want to have something like, okay, so this was based on a snapshot across the North Atlantic oceanic region, which has a 9 square kilometer region, and we assumed here 900 or 1800 planes across the whole 9 million square kilometers, which is a relatively low density down here in the bottom left corner. So you can see here that the lowest density scenario is we would have like 20 planes with almost 100% probability. And if we have a higher altitude of, say, 11 kilometers, that makes quite a bit of difference. You see that it increases the number of planes to about 30 from 20. And if we double the density, then you could have as many as like 60 or so planes. So essentially, we can actually generate a model for this. And I think this is something which, for example, Leila can handle extremely well, because she does a lot of clever networking research. So looking at the applications very briefly, obviously there's the air traffic control, which is the ultimately most important link, but the bitrate requirements are relatively low. Whereas when you look at, for example, entertainment, then the bitrate requirements are quite high. And so, the network is extremely heterogeneous. So you still recall probably that we had these kind of 3-4 layers on top of each other. We had the terrestrial layer, then we had the drones, and then we had the planes, and then we had the low Earth orbit, the medium Earth orbit, and the geostationary satellites. And they also use rather different frequencies. I'll come back to that in a minute. There are actually lots of standards on this, but they are not linked to any of the terrestrial systems apart from a few examples, like, for example, the German system, which relies on the fourth generation LTE system. So you could also learn from the migratory birds because they fly information in order to save energy, basically. And the so-called square-headed ducks, amazing species, they can actually fly over the Himalayas, imagine, in that thin air. And the way they do it is they fly information. And then military aircraft, of course, routinely fly information, again, not just to save energy, but it looks also very tidy and fantastic, really hard to believe. But you need very, very tight control. But there's nothing to stop us from doing this for passenger aircrafts either. Currently, they are really limited to be to be beyond 5 aeronautical miles in order to avoid any accidents. So that was a little bit on the services side and application side of things. I always remember, Rahim's astute remark that we have to have a use case and then people would pay for it. And so in the US, they already have many, many carriers who actually provide internet services at good quality and at a reasonable price as well. So let's look at some of the specifications. And this is really a sort of more sophisticated version of Rahim's triangle, Rahim's 5G and 6G triangle. But, just pick two of these aspects here, immediately becomes obvious what I mean by this. The throughput and the power efficiency are obviously, in a juxtaposition to each other. And so in this context, I can always increase the throughput if I opt for higher throughput, higher order modulation schemes, but I need much more power. And so, in terms of latency, again, we can reduce the latency if we increase the bandwidth, right? I can double the bandwidth, I can then transmit at twice the speed, and I can download a file in half the time. All these things are kind of plausible. And this is the first time where I want to delve briefly into the multi-component objective functions. So if you are like a PhD student, for example, you might find this an inspirational research opportunity because, when we talk about trade-offs, that's like swinging a pendulum between power efficiency and power efficiency, as we discussed. But in reality, what we want is to have the so-called optimum Pareto front of all optimum operating points where we cannot improve, for example, the bit error ratio without increasing the delay because we have a longer channel code, or because we iterate more in a turbo receiver, so we increase the complexity. And this is really a next generation challenge. The way this was solved in the 5G systems, of course, is that we now have the machine-to-machine communications, we have the ultra-reliable low latency mode, and we have the enhanced mobile broadband. But in reality, these are, again, rather different operating modes, and we ought to be able to have a transceiver that is reconfigurable across all these different parameters. So I mentioned the frequencies, and millimeter wave research has come a very, very long way. And the beauty of communicating above the clouds is that we don't really have, sort of obstructing objects, solid obstructing large-bodied vehicles or buildings like we have in terrestrial communications. So, in fact, NASA is also looking into using millimeter wave frequencies where large bandwidths, large chunks of bandwidth are available for aircraft to aircraft communications. And then, of course, we could have free space optical up to the satellites, for example, which could be used also as a backhaul. So these are just really to show you a set of acronyms. These are the standards, and some of them, well, in fact, literally all of them are rather antiquated, especially the aircraft to ground and aircraft to aircraft standards. The aircraft to satellite, obviously these are coming back again. And I heard that ICC that it costs about 10 billion US dollars to keep the low Earth orbit satellite network going. So obviously you need, again, use cases for this. Otherwise, it will remain unsustainable as it was in the first round when they stopped these services. So moving on, really, I'm conscious of time. So just to look at some of the enabling techniques and, the Pareto optimization problems that I mentioned, so that we cut out some interesting research issues as well. And, we could almost imagine being in a conference setting with Claude Shannon. I'm old enough to sort of see him in action. But never been to the same conference as him. But, Rahim mentioned so many challenging research issues, and I'll drill down a little further now in this context. Many of you would know the Gupta-Kumar law, which basically says that the per node capacity of large ad hoc networks tends to zero, because effectively, if you have a plane up there which is just relaying in an ad hoc network all the time, it can hardly ever transmit its own messages, right? So the more nodes you have, it's a bit like Chinese whisper, somebody whispers in one ear, you pass it on, and then the next message comes, etc. So it's very plausible that the capacity of very large networks on a per node basis is low. And of course, there's, interesting research questions, for example, in finite block length information theory and the corresponding channel codes and modems and ARQ. It's another manifestation of improving the integrity, namely reducing the bit error ratio at the cost of course, increased delay, because we have to repeat the messages, etc. So, network information theory is not so mature, really, despite the amounts of research funding invested into this field. And that goes also for ad hoc networks. So this is another slide where we could spend hours and hours talking and debating. And as Rahim said, it's very wise to refrain from sticking key performance indicator figure on bit rates or delays and so on, unless we actually have the use cases. But of course, everything will be controlled still by Shannonian laws, only that I sort of modified this, and you have here the SINR rather than the SNR. And so it's obvious that if we want to increase the capacity by increasing the signal to noise ratio, this is behind a logarithmic function. So you have to really exponentially increase the power in order to get a linear increase of the throughput. By contrast, if I use large-scale MIMOs, for example, then I can linearly increase the capacity with the number of antennas. And that's probably really the sort of reason for the spectacular success of MIMO schemes. There's a lot more in this slide, but I won't talk too much about it right now, because I just want to really entertain you rather than bore you with very detailed discussions. But the frequency choice of the frequency is vastly important, as we discussed. And so we have pushed lots of things now to ever higher carrier frequencies because we have more bandwidth at higher carrier frequencies, as goes without saying, really. And then in the millimeter wave band, the 28 and 38 gigahertz turned out to be fairly popular. But of course, we can use the free space optical communications links for satellites and visible light within the planes, for example. Imagine having your little light, the reading light above the seat, and whilst giving you light at the same time, it could be also transmitting entertainment information. And, this way you could actually get rid of all the wiring required for audio and entertainment as such, because we already have the electric wires there. And in its simplest form, you could just flicker the LEDs above the fusion frequency of the human eye, and that would give you megabits per second rate. So it's actually also quite feasible to do. But again, just wanted to draw your attention to this issue. And when we're talking about aircraft communications, the three component sort of power budget design figure in this slide obviously can't get rid of the path loss, but we don't have log normal shadow fading. And indeed, even the fast fading is typically more benign, because you might only have a reflected wave from the ground, and that's a relatively long delay reflection. So let me show you a sort of snapshot of the four different scenarios which I mentioned, just really to sort of remind you. Earlier on, we looked at these scenarios, so taxiing, taking off en route, and then landing, taxiing, parking. And so now we try to look at the associated channel qualities. And here we've got the attenuation on the vertical axis, and here we have time on the x-axis, and then we have frequency on the y-axis. And so en route, it's almost like independent fading. So you could actually go away and write down equations on this basis. But as we slow down, for example, arrival scenario, you see that the time and frequency distance, hopefully you can see my cursor here moving between these troughs, is ever so much extended. So now it's becoming more realistic to actually estimate the channel. In this scenario, the channel fluctuation is so fast that actually non-coherent detection would work better, because otherwise you would need so much pilot overhead that ultimately the non-coherent detection would outperform the coherent pilot-aided detection. And this is the taxiing and parking. So just really a bit of a subjective picture on the associated channel qualities. And in this slide, what we can see here is on the left-hand side, I now go back to Shannonian capacity, and we have the spectral efficiency in bits per second per hertz. And this is down at the x-axis is the distance. And so as we are farther and farther from the source, the adaptive modulation encoding mode starts to have lower and lower throughput. So what we have here is, based on the capacity estimates, a throughput between 2.7 and 0.46 bits per second per hertz. So the dilemma in this context is becoming probably quite clear later on as we go along. But let me highlight it right now, is that you could have an ad hoc network where you hop your messages all the way from London Heathrow, for example, to JFK Airport in New York, so that you hop it over shorter distances, in which case you can have a higher throughput. However, because of the sort of excessive relaying, the delay would be relatively high as well. Or alternatively, you could have much longer hops, and this is a routing design issue, of course. You could have much longer hops, and hence you would have less hops from London to JFK. However, the throughput would be much lower because the distances are much lower, so the receive signal quality would be reduced by the large path loss. So, all the classic physical layer improvements could be used. In this context, the most popular research topic is, of course, the massive MIMO systems. And you would think that there is a huge, lots of space on the aircraft wings, but it's actually still a challenge to find enough space because you want to be able to communicate upwards to the satellites and downwards to the terrestrial users or ships, etc. And then, of course, there's the control antennas, and they will use different frequency bands, so they need different types of antennas. So you would really need multifunctional antenna arrays, which can also be reconfigured to operate as a blast type scheme for spatial multiplexing, or a space-time coding scheme for achieving a diversity gain, or alternatively as for example, a beamforming scheme, which is quite crucial for millimeter wave systems. And this would allow us to get, closer to Shannonian capacities, provided that we use one of these multifunctional MIMO systems called, for example, layered steered space-time coding, which has a certain number of antennas dedicated to beamforming, lambda over 2 spaced elements. Then you would have another chunk of those or other clump of those relatively far away within the same large array, which would be fading independently, so you could use it for space-time coding and alternatively also for increasing the throughput. So I'm coming to the last topic really, which is this challenging optimization problem that I've been banging on about as we were sort of proceeding. And, in the end, the funny thing is we started this research in the quantum communications research area because quantum search algorithms have a complexity that only grows according to the square root of the number of nodes in a large atomic network. And then later on, we also introduced it into classical communication systems. So what I will be looking at is gradually increasing the grade of challenge as we progress. So I will not be looking at all these 4 components, for example, but we've got some tutorial papers on these topics. The associated design trade-offs, I already mentioned this, but I will just draw your attention to it again very briefly. So you have here, London Heathrow, and you have JFK in New York here. So you could have a larger distance between the source and the destination in an atomic network. I only use here, obviously, a 2-hop and a 3-hop path, but the 2-hop path has much longer hops, and therefore it needs more power, whereas the delay is reduced, especially if you use, for example, decode and forward relaying, because it has to be decoded and then re-encoded. So every hop would add an extra 10 millisecond or 20 millisecond delay typically. And the top path here indicates that you have more nodes in the routing procedure. However, these are shorter, so you need less power, but you will end up with a higher delay. And so really just to show you an interesting use case, which was related to the Australian scenario. As you know, much of Australia is really, again, desert in the middle, but if you've got highly or densely populated areas at both the east and west coast, for example, Perth and Sydney. So what we did, we looked at the 5 most busy airlines in Australia. Took us a long time to collect the data. And you see here that, for example, Qantas would have 374 flights on the 29th of June back in 2018, which was the busiest day of the year. Virgin Australia, a bit less, Jetstar, Tiger Air, and then Rex, the Regional Express. And we also looked at the least busy day, which was Christmas Day. And so we collected statistics, bear in mind these 2 different scenarios as we go along. So what we did, we tried to look at rigorous distribution fitting in order to find out, for example, the number of flights in Australia in the air on these 2 days. And so this is the number of flights here, and this is the hour of the day. And this is left-hand side, the least busy, and right-hand side, the most busy day. Now, I already showed you something similar for the North Atlantic region, but here we have the real flights indicated by the black lines. And here we have the normal distribution used to model this data. And we have the Weibull distribution used for modeling this data. We looked at about half a dozen different distributions, but these 2 fitted best. And so what we did then is we ran investigations based on the true flight data, which we collected, and the model data based on these 2 distributions. Another important statistical feature of the Australian scenario is basically the takeoff times. And so you here at the top, you see again the real flights, their distribution between 5 in the morning. In fact, there's a takeoff around about 3 in the morning or 2 in the morning. And on the right-hand side, we have again the busiest day. And oh, actually, I've got it the other way around. Apologies for that. So the right-hand side is the busiest. You see here, this peak is about 80, and here the peak is only about 50. And then we have here the normal distribution, we have the Weibull distribution. And so the last thing I really want to show you is this multi-component optimization problem solved, where in this specific scenario, we looked at initially just 2-component optimization. And again, this was now finally a European scenario, so that we have, the North Atlantic, Australia, and Europe. And this was British Airways flight taking off from Istanbul Airport, again on the same day in June the 29th. And on the vertical axis, you see here the path lifetime. On the horizontal axis, we have the delay of the aircraft to the ground station or to the airport where it took off from. And so you see here that we have either 4 or 5 or 6 hops. And so if your Pareto optimization objective is to basically have the minimum possible delay, then you would opt for these longer hops, but unfortunately, the throughput would be more limited. The path lifetime would be more limited. And this unique point here at the right-hand side indicates that you could have 6 hops, but the delay would be, instead of 60 millisecond, it would be 80 millisecond. And so that's the first manifestation. And then the final result, which I really wanted to share with you, is this one, where we actually looked at a 3-component optimization. So let me be absolutely clear. This is not constrained optimization where we just optimize, for example, the throughput, and then we set a maximum power limit or a maximum delay. It's jointly optimizing all these. In other words, finding all the Pareto optimum solutions. So all these little dots, again, the blue dots, actually indicate the full set of Pareto optimal solutions to this optimization problem. And so again, you could look at, say, a point here and read out the performance. So if I look at, for example, the throughput is about 35 megabits per second for this point, and we are 2 divisions up. So we have 10 minutes for the path lifetime. The trouble with this is that every 10 minutes you have to hand over, and this handover is always problematic, as we know from terrestrial communications, because there may not be a free channel anymore, but the desired link is becoming, unfortunately, too degraded. And so the other extreme would be this corner, where again we can have a path lifetime up to 40 minutes. That's really nice, no interruptions, no handover problems, etc. But the trouble is that the throughput would be only 20 megabits per second, and the delay would be like 80 milliseconds at this point. So I think, there's this huge array of things I haven't even touched upon, and I won't even attempt to sort of summarize these things. Ultimately, what I would like to leave you with is the message that, the single component optimization era is kind of almost over. Rahim and I worked together in the Virtual Center of Excellence in Mobile Communications, and many years we worked on near capacity systems. Then about 10 years ago, well, a bit more now, but we switched to green radio, which we coined that terminology, and basically we looked at power efficiency. But this is like, swinging again a pendulum. And so instead, now we're going to have to really look at finding all the trade-off points, all the joint optimum points. And that's going to be a while for all of us. And this is totally independent of whether we're talking 3G, 4G, 5G, or 10G into the future. So with this, thank you so much for listening. And